Today we're going to talk about thin film interference. You've probably noticed colorful patterns in things like DVDs and soap bubbles and even sometimes in puddles. And each of these involves a thin film. So there's a thin clear film over top of a DVD, and underneath that is a mirrored surface. The soap bubbles, of course, have a very thin film of soap, and then air on the outside of that film and air on the inside of that film. And in the case of a puddle, where you see a colorful pattern, it's because some oil, usually from cars, will float on top of the water. So you have a very thin film of oil on top of the water. So why might these thin films produce interference patterns? Well, let's think about that. Let's say we've got a thin film down here. Maybe it's a soap bubble. And light is going to come into that soap bubble. Some of that light is going to be transmitted through that first surface, and some of it would be reflected by that first surface. And then this portion of the light that was transmitted, it would be partially reflected and partially transmitted into the interior of the soap bubble. But the key feature here is that we've got one ray coming in, but we've got two rays going out because you've got the two reflections. And of course, two waves can interfere with each other. So it's those two reflected rays that produce that interference pattern. And generally, for a soap bubble, this is going to be quite complex because you've got white light coming in, which is a broad spectrum of wavelengths. So you're going to have all kinds of phase relationships between the two reflected rays. And even when you change your angle of orientation, so you're not looking at the bubble from the same angle, the fringe patterns will all shift because that's going to change all the phase relationships, because effectively this distance is going to be longer than this distance here. And then of course a soap bubble changes in size. They generally expand and the soap becomes thinner and thinner. And that also changes phase relationships. So you have these constantly changing phase relationships that produce a really interesting, colorful pattern on the soap bubble. Now those crazy patterns on soap bubbles are just too complicated for us to analyze. So we're going to start with the simplest case first. We're going to have a nice, even, thin film. And we're going to send some light in perpendicular to that surface. So it's going to come in perpendicular, but I'm not going to draw it perpendicular, because if I do that, then the incident ray and the reflected ray lie right on top of each other and everything looks all mushed together and it looks too confusing. So I'm going to have it come in at an angle. And as you can see here, I've got a constant wavelength. That means I've really got monochromatic light here. So I've got light of one wavelength coming in. That's going to simplify, and we've got monochromatic light of one wavelength coming in. It will change its wavelength slightly as it goes into that thin film. Some of it will be transmitted and some of it will be reflected. Some of it will be transmitted and some of it will be reflected. And so here's our two reflected rays that are interfering. Now if we look straight down at our thin film, and these two are exactly out of phase, then that thin film would look dark. And if we look straight down and these two reflected rays were exactly in phase, then our film is going to look bright. And if we could somehow gradually increase the thickness here, these two reflected rays should go in and out of phase. So you'd see the film go dark and then bright and then dark and then bright as you somehow gradually increase the thickness of that film. Or let's say that you had your film gradually increase its thickness, like so. Then you should be able to look down and you would see fringes across the film that would look something like this. This is achieved using an air wedge. You've simply got two pieces of glass, and then you've got something stuck in between the plates at one end. So there's a gradual change in the thickness of that air layer, constantly changing the phase relationship here so that you get dark and bright lines, much as you see with a two-source interference pattern. So now we need to think about, well, what creates the phase difference between the reflected rays? So let's imagine here's our thin film. The incident ray comes in, some of it gets transmitted, and some of it gets reflected. And some of this ray will also get reflected. These two are going to interfere. So the first thing that's going to create this phase difference is just the fact that this ray here is traveling an extra distance. It has to travel the thickness of the plate, and then it has to travel back again the thickness of the plate. So the first contributor to this phase difference is this extra distance traveled by this reflected ray. The second contributor to this phase difference occurs here and here where we have the reflections. Some reflections produce a 180-degree phase change. Some reflections don't produce any phase change at all. So the second contributor would be the nature of the two reflections at the two interfaces. And we've already talked a little bit about the nature of those phase changes at reflections. So hopefully you recall when we were looking at slinkies and springs, we could send a pulse in and hold one end of the slinky fixed, and the pulse would get inverted. It would come back on the other side. That inversion is really a 180-degree phase change. And then we began to attach the slinkies one to another. And if we were to attach a heavy spring on the other side, so this is a heavy spring, then we'd still get this 180-degree phase change because of the inertia of that heavy spring. Some of the pulse would be transmitted through, but the reflected part would go through a 180-degree phase change or an inversion. But it also works for the media that light travels through. What plays the role of the heaviness of the spring? Well, the index of refraction, the optical density. So we can say this: if light travels into a more optically dense medium, that is a higher index of refraction, then the reflected ray undergoes a 180-degree phase change. And likewise, if we go into a lighter spring, or in the case of light, something with a lower index of refraction, then this reflected pulse is not inverted. There's no phase change. So if we've got a thin film here, whether or not we get constructive or destructive interference depends on the phase relationship between these two reflected rays. And the first source to any phase difference there is caused by this extra distance here. Once through the thickness of the film, and a second time through the thickness of the film. So this distance here of 2t contributes to the phase difference. Now, phase difference, keep in mind that we always measure the phase difference in wavelengths, really in cycles of a wave. So what we'd like to know here is how many of these wavelengths fit into the distance 2t. So our path difference is simply going to be that distance divided by the wavelength. How many of those wavelengths fit into that distance 2t? Now, be a little bit careful here, because the wavelength we're talking about is the wavelength in the film. So I should put F film here. Now, we're not going to know the wavelength in the film directly. We will have some sort of source of light, and the manufacturer will suggest a wavelength for that light. And that will be the wavelength in air. So this lambda in the film is going to equal that manufacturer's value of the wavelength really in air, divided by the index of refraction of the film. So we can write our expression here for that path difference created by that extra distance traveled to be equal to 2 times the thickness of the film divided by the wavelength of the light times the index of refraction of the film. Now the next thing we need to do is figure out any contribution to path difference due to those inversions at the 2 reflections here and here. Now let's look at the path difference due to the reflections at the interfaces. So let's look at 3 scenarios. So I've got thin film 1, thin film 2, and thin film 3. And let's say in the first case we're going from air, where the index of refraction is 1, to water, where it's about 1.3, to glass, say, where it's about 1.5. So we're going from low to high optical density. So that would mean we're going to get an inversion, a 180-degree phase shift at that first interface, and we're also going to get one at the second interface. In both cases, we go to a more optically dense substance. So in this case here, we have 2 inversions. So just due to the inversions, this one got flipped upside down, and this one got flipped upside down. There's no relative change in the phase. If we have 2 inversions, we're effectively back to our original starting place. Let's consider thin film 2. So this time, we're going to go in the opposite direction. We're going to go from optically dense glass to less optically dense water to less optically dense air. And that means there is no inversion at the first surface, and there is no inversion at the second surface. So because you have 0 inversions, once again, you get no effect. And that's kind of what you're expecting anyways, because we're just running the rays in the opposite direction here. Now let's try a third case. Look at our third thin film. And this time, let's make it a soap bubble. So we're going to go from air n equals 1 to soap n equals 1.3 back to air n equals 1. So at the first interface, we do get an inversion because you're going to more optically dense, but at the second interface, there is no inversion because you're going to less optically dense. So what's happening here, it's like when you add 180 degrees, when you flip the wave over, you're effectively adding or subtracting half a wavelength to the path difference, right? If I have a wave like so, and then I draw it upside down, it's the same thing as if I had advanced the crest by half a wavelength. So this is the same as adding or subtracting half of a wavelength to the path of the wave. So we can represent this situation here by simply adding 1/2 to the path difference. So let's now try to pull this all together, and we're going to try to come up with a formula for the conditions where you get a dark fringe, where you get darkness or a minima or destructive interference. And it's going to be for the case where we've got one inversion from the 2 surfaces. So if we're going to get destructive interference, then our path difference has to be a half integer number of cycles. So it's got to be, say, 1/2, 3/2, 5/2, etc. Or we could say it's half of a wavelength, 3/2 of a wavelength, 5/2 of a wavelength. But of course, the path difference is measured in wavelengths anyways. Now we're going to want to write this as a formula. So I'm going to write this as m plus 1/2, where m is equal to 0, 1, 2, etc. Now this path difference has to come from 2 contributions. And it's the same 2 contributions we were talking about earlier. One due to the thickness, and 1 due to the phase inversion at one of the surfaces. And that throws in an extra half of a cycle, or we could say a half of a wavelength, but the path difference is measured in wavelengths. So the path difference that we've got to get has to come from the sum of those two contributions. So we can subtract a half from both sides, and we'll get that m lambda is equal to 2t times the index of refraction of the film, where m equals 0, 1, 2, etc. So there is our condition for destructive interference when we have one inversion. Let's work through that reasoning again, but this time we'll apply it to where we get a bright fringe. Once again, it's going to be a case where we have one inversion from the two surfaces. So for a bright fringe, that means we've got the constructive interference. And we get constructive interference when our path difference is equal to 0, 1, 2, etc. full cycles. Writing that as a formula, we'd say that that was simply m, where m equals 0, 1, 2, 3. So this path difference that we have to get comes from two contributions. Once again, same contributions, one due to the thickness and one due to that single phase inversion. And an inversion always throws in an extra half of a cycle. Now it really doesn't matter whether we add in an extra half cycle or we subtract off a half cycle, because we still end up at the same place in the phase. I'm going to subtract off half a cycle, and you'll see why I'm going to do that in a second. So once again, that path difference that we have to end up with comes from the sum of these two contributions. Now I'm going to add a half to both sides and then multiply by the wavelength. So I'll get that m plus 1/2 times the wavelength will be equal to 2t times n film, where m equals 0, 1, 2, etc. So the reason that I wanted to use a negative 1/2 here is so that when I put in m equals 0 here, 0 minus 1/2, which would give me a negative number of wavelengths. So I just don't want to confuse myself with negative numbers, and that's why I read it this way. Now those two equations that I just derived are given in the IB data booklet. The only difference is that for the thickness, the IB likes to use a D, whereas me and many other textbooks like to use a T for thickness. And take note, they don't give us the equations for when there's 0 or 1 inversion. But all you have to do to get the 0 or 1 inversion equations is interchange constructive and destructive. So the destructive interference equation would be this one, and the constructive interference equation would be this one.
Okay, here's one for you to try. Pause the video, read the question over, try it out for yourself, come back for the answer. In this case here, we've got a thin film with an index of refraction of 1.76. And then we've got glass on either side of it with an index of refraction of 1.51. So our interference is going to occur between these two reflections here. And we want to work out what this thickness is, such that we're getting strong reflection. If it's a strong reflection, that means we've got constructive interference. And note here, we have one inversion here, but we don't have an inversion here. So this is a case where we want to use our one inversion equations. That is to say that for constructive interference for brightness, lambda times m plus 1/2 should be equal to 2 times t times the index of refraction of the film. So rearranging for t, I'll get that t will equal the wavelength times m plus 1/2 all divided by 2 times the index of refraction of the film. Putting in my numbers, I'm going to take a first case where I set m equal to 0. So this is going to be the minimum thickness at which the condition is satisfied. My wavelength, I'll just write that as 500 nanometers. I won't switch to meters because the other quantities in my equation here are unitless. So I've got 500 nanometers times 1/2 divided by 2 times the index of refraction of the film, which is 1.76. Work that out, and I get a thickness there of 71 nanometers. Now that's not the only thickness that will work. I could also put an m equal to 1 in here, and I get a second value. That should come out to be 213 nanometers. And if I do a third value, I'd get 355 nanometers. So this second value here is 3 times as big as the first value. And this value here is 5 times as big as the first value. Another example for you. Pause the video, try the question, come back for the answer. So in this case, we've got light coming into a solar panel with a thin film over top of the cell itself. So we're going from air, which has n equals 1, to this layer of silicon monoxide where n equals 1.45, to the cell itself, which has a very high index of refraction, 3.45. So incident ray and the 2 reflected rays. Notice that on both reflections, you're going to a higher optical density. So you're going to get an inversion here and an inversion here. 2 inversions, they cancel each other out, essentially keeping the same phase relationship between those 2 reflected rays. So we're looking for the minimum thickness, so that means we want to take m equal to 0 here. And we also want to minimize the amount of light that is reflected. In other words, we're looking for a dark fringe. And that means our path difference should be equal to 1/2. Remember that path difference is being created by the extra distance traveled, 2tn divided by lambda, plus any additional path difference created by the inversions, but we don't get any of that because we've got 2 inversions. So we end up with 1/2 equal to 2tn over lambda. If I solve for t, I'm going to get that it's equal to lambda divided by 4n. Substituting my values in there, I've got 550 nanometers for the wavelength of the light. I've got to divide by 4, and I've got to divide by this 1.45. It's the index of refraction of the film that goes into the formula. Work that out, and you should get an answer there of about 95 nanometers. So this minimum thickness of the film, such that you're going to get minimal reflection, and that means maximum absorption of the light, is going to occur for a thickness of 95 nanometers. So let's summarize the big ideas from the video. If we consider our simplest situation where you have a uniform thin film and monochromatic light, then our path difference for the 2 reflected rays is going to either equal a half integer value, m plus 1/2, or a full integer value, just m, where m's an integer. If it's a half integer value, that's destructive interference. That's dark fringes. If it's an integer value, it's going to be constructive interference. And this path difference is being generated from 2 sources. One source is because of that extra distance that the 2 reflected rays travel. And that's given by that total distance traveled divided by the wavelength in the medium, which will equal the wavelength in air divided by the index of refraction of the film. Plus, we can also get some path difference generated because of the inversions at the interfaces or surfaces of the film. And that's either going to produce a path difference of 1/2 or 0. If it's 1/2, that's because there's one inversion. One surface that goes from a lesser to a greater optical density or index of refraction. But there won't be any change in the path difference if we have 0 or 2 inversions. So our end result is going to be m plus 1/2, or simply m, depending on whether it's constructive or destructive, will have to be equal to, in all cases, 2t times the index of refraction of the film divided by the wavelength of the light, plus 1/2 or 0, depending on whether you have one inversion or 0 inversions. The IB does give you these formulas here. Just remember, these two formulas are for when there's one inversion. If there's 0 or 2 inversions, then you can simply interchange the word constructive for the word destructive here and keep the same formulas. So if there's 0 or 2 inversions, simply exchange constructive for destructive. And that's all for today, folks. Thank you very much.